Okay, time flies. It's last two sections in chapter 8, and we are going to have a review test next week regarding chapter 8. Okay, and for those you use the brief version, that is the red cover, you don't have 8.7, but instead you have 8.6. That's the same material. However, you don't have an 8.8, so you had to make some kind of a arrangement to cut the textbook. And so 8.6, 8.7 in the core version is the same as in the brief version, 8.6. Okay, it's called double integral. And double integral is similar to the integrals we learned before. However, we have two variables, so we call double, means variable have been applied twice. Okay, and let me brief a little bit about what is the double integral really referred, and use the geometric point of view. So the function, as written in one variable situation, we use height, the function value, multiplied by the width to represent the area of a rectangle. And the interval we evaluate have been partitioned into several rectangles, and so that become the whole area become the sum of the rectangles, and that particular sum is proposed by Riemann, so we call this Riemann sum. And take a limit of this limit if exists, then we name this one as the definite integral, and that was what we learned in chapter 6. Okay, the integral. And for the double integral, the domain we're looking for is not only a line, it's actually an area. And here use a simple situation, rectangles, the R as our region. And so what we evaluate will be still using the same idea, and we partition our domain, the rectangle domain, into a little bit smaller rectangles, and the area of the rectangles multiplied by the height, that is the function value. Then we have the volume, and the summation of all this volume again is called Riemann sum. And so the Riemann sum all of this together, and the height multiplied by the width and length of our subrectangles, and become the volume of this small part, and add up all together will be our Riemann sum. And here we have two different dimensions, and may not necessarily cut into the same amount of subintervals. So we use n as the intervals for the first dimension, and use use m as the dimension of the number of the first subintervals, and use n as the number of subintervals in the second dimension. Okay, so altogether we have m multiplied by n, that many rectangles, and multiplied by the height, corresponding height, form up the summation of this volume. And this volume will be a very good approximation of the volume for the whole surface. Okay, and that is known as the definite integral for two variables, and we call this double integral. Okay, and to evaluate that one, it's different story. Basically, the idea we just mentioned, we partition our domain into small rectangles, and use the Riemann sum to do the approximations. And hopefully, the limit for this approximation, the limit means the subintervals become infinite many of the subintervals for each dimension, and then we were expecting the Riemann sum will be a good approximation of the double integral. And that is the definition for the double integrals. Okay. However, when we try to do the evaluation, we cannot do it in that way. So we have to come up with some kind of a technique. And here is called the iterate integration. Okay. So to evaluate, we do the integration one by one. Okay. Still, the definition for double integral is send us to evaluate the volume of this surface. So, but when we try to do the evaluation, we doing variable one by one. And in this case, in the equation number 19, we do the evaluation on x variable first. And in that situation, y is treated as a constant. Okay, so we only deal with x. And since deal with x, so even though the function is still in the two variable function form, however, it have been treated as one variable. So all the technique you learned in chapter 6 is applicable. And then you can evaluate this part as the definite integration we learned before. And since you plug in the lower limits and upper limit for the x from a to b, therefore the result of this definite integration become no x at all. The only unknown variable left will be y. So inside the quote is a new function with variable y. Therefore, you can evaluate the definite integration with variable y. Okay, and that is called iterated integral. That is, we do the integral twice, starting from x, and after you finish the integration of x variable and become function of y, and then you do the integration on y only. So you'll come out with constant value. Okay, right. And since every time you deal with one variable, so you might have a choice which variable come first. Are you going to do dx dy as they mentioning here, or you want to do dy dx? Okay, and so they have some kind of a exercise and also the formula to deal with that one. And let us focus on this process, doing one variable at one time, and use dx. We come out with a new function called g of y, and then do the integration of g of y on the second integration process. Okay, so we try to learn this using the following exercise, and this is exercise number 4, and I choose from the backup book. And right here, x is given between 0 and 1, and y is given between 0 and 2. So let's try x first. So the integration oops. Oops, what happened? I couldn't change it. Okay, well, anyway, I cannot change color, so I'm going to use red color all the time. Okay, so the integration, the function is 12 x times y squared plus by a times y to the power of 3, and dx dy, and since x is between 0 and 1, so then we have between 0 and 1, and y will be between 0 and 2, so then we have a 0 and 2 in here. Okay, all right, now the first step, since I'm dealing with the variable x, so 12 y squared is the constant coefficient of x variable, and the antiderivative for x is 1/2 of x squared for the first term, right? In the second term, the whole a times y to the power 3, it's a constant. And the integration of a constant is simply x. So I have x. And the plug in will be from 0 to 1. Okay, and dy. So in the first step, we finish our integration on x only, and 0 to 2. Now let's find the result. For the first term, 12y to the power of 2. Okay, and plug in 1, we have 1/2. Plug in 0, we have 0. So the result after plug in, the lower limit and upper limit for the x is become 1/2. So that's the first term. In the second term, we have 8 times y to the power 3, and x from 1 to 0 become 1. dy. Okay, so as you can see, what happened to here? Here we have a new function which involving variable y only, has no more x. Okay, because we have been substitute the x by plugging the lower limit, upper limit into the subtraction. So no longer variable x. Okay, and the only variable left will be y. And since now it's a variable x, so we know, variable y. And the first term, 12y squared multiplied by half, so we have 6y squared. And the antiderivative for 6y squared become 2 times y to the power 3. So that's the first term. And the second term, 8 times y to the power 3. And the antiderivative for that will be 2 times y to the power of 4. Right? Okay. Now what are you going to have? 0 to 2 as the lower limit and upper limit to be plugged in. Okay. Now the final result. 2 times 2 to the power 3 minus by 0 to the power 3 plus by 2 times 2 to the power 4 minus by 0 to the power of 4. So it's 16 plus 32. So we got 48. Okay. It's quite simple. As long as you make a decision about the integration ordering, in this case we do dx followed by dy. Okay, and each time the evaluation starting from the inner part, we do this integration first, and after that you have only one variable left, and then do the follow integration again. So it's called iterated integral. Okay, and double integral means we are going to do that twice. Okay, and your exercise, I can expect you can do that by using that, saying that try use different order. 12xy squared plus by 8 times y cubed dy dx. Okay, so in that case, you should starting from 0 to 2 in the first integration process, and then starting from 0 to 1 for the second integration process. Okay, so try that, okay, by yourself to see what happens. Okay, and any questions? Okay. All right. Now, most of the situation, the double integral won't be that easy. Okay. And the key will be the domain of our integration. Say the R. Okay. In this case, the R is a rectangle regarding x from 0 to 1, y from 0 to 2. But sometimes the domain will be some kind of a irregular region form and can be described by function. So in that situation, the evaluation using the iterative method will be different story. So here in the book, they give you in the serial number 1 two major kind of integration region. Okay. In case of the first one, in that type of a region has upper function and lower function described by y equal to g2x and y equal to g1x. So it's a function of x for y. Okay, and since this region is a two-dimensional region, so we expecting one variable can be expressed in terms of the other variable. Okay, so in the case, if your region can be described in terms of two functions and using the x, okay, then we are going to apply the order of dy dx, the order of dy dx, meaning that we fix x first, and y we're starting from the lower to the higher, so y we're starting from g1 function to g2 function. So the integration form will be from g1 to g2. And you might notice that when we do the integration with respect to variable y, x is a constant. Our upper limit and lower limits in this integration has no y, only x. Okay, so for the y variable, g1 and g2 is a constant for any given x. Even the form looks like a function, but still a fixed number. Okay, and so you can do the regular antiderivative form using the variable y. And after you got the antiderivative, you plug in g2 minus by plug in g1. So you come out with a new function on x, and then doing the integration on x. And this time x will be from a to b, so your limit for the x integration will be from a to b. Okay, so this is the first type. In the case, your domain of the integration can be expressed in terms of function on x. Okay, but sometimes you might encounter the following situation in here. The function or the region is a curve. However, this curve is not a regular function type. Instead, it's a function of x in terms of y. So the x can be expressed in the lower function, lower curve, h1, h sub 1 of y. And in the upper case, x equal to h sub 2 of y. So x and y will be a function of x. X will be a function of y. So in that situation, we are going to use the order in number 21. Fix y first. Fix y first. And then x will be integral from this button, from the left to the right. Left is g1, h1y. Right will be h2y. So the integration will be from h1y to h2y. And the possible fixed y value, we're starting from C to D. Okay, so our D, our y will be starting from C and up to D. So our integration limit can be written in this format. Okay, and once double integral can be rewritten in terms of the iterative integration with a choosing order, either number 20 dy dx or number 21 dx dy. As long as you make a choice, then you only deal with one integration for each time. Okay, and that become applicable. All right. Okay, and this is these are the two major domain type, but sometimes the domain is more complicated than that. So we'll try to split your domain into possible several combination of these two types, and each one deal with them one by one. Okay, and that is how we end up with evaluating the general situation of the double integrals. Okay, and our example was using obvious easy one. So the first function, the double integral we are going to evaluate is number 12. Okay, and the function is simple, equal x times y, two variable functions, and so we need to know what is the domain of our integration focus on. And so you have to plot this description. Is say that R is bounded by x equal to 1, y equal to 0, and y equal to x. Okay, so let's try to draw the curve for this one. Okay, this is x, this is y, and x equal to 1. So this is x equal to 1. Okay, so this is x equal to 1. Okay, and we also have a y equal to 0. So this is y equal to 0. Oops. Okay, and y equal to x. Y equal to x is a line 45 degree, y equal to x. Therefore, we have intersection 1, 1. Okay, and it says that R is bounded by these three lines, one vertical, one horizontal, and one a little bit has a slant. Okay, so the region should be something in between, enclosed by these three lines. So that's a region R. Okay, all right. Okay, now it's an option. Which order you are going to do the iterative integration? Okay, and well, it might be easier to using the dy dx. Okay, it might be easier. So let me try to find the order dy dx. Okay, so option 1. Dy dx. Okay, and let's try it. Dy dx, meaning that x should be fixed. So x is given in here, and your y should be starting from the bottom to the top. Okay, so your y rate starting from 0 to x. So you have from 0 to x. Okay, and what kind of x you can change? The interval of your possible choice of x will be starting from 0 to 1. You can choose your x among 0 to 1. So your x will be from 0 to 1. Okay. And after that, the integration is quite straightforward. Do the integration of y first. Okay, and I'm not going to do any further, and the following exercise will be yourself, you're practicing, and I'm going to give you option number 2. Now I'm going to change the order. Instead of dy dx, I'm going to do dx dy. Okay, and remember when we say dx dy, meaning that we are going to do the x first. So the y will be fixed in the first integration. Okay, so y fixed, meaning that your y should be picked up as a given number in here. Okay, and as long as your y choosing then what will be your x goes? X will go from the left to the right, right? And since your left is on the line of y equal to x, so that means your x should be starting from y, since y is given, right? Y is given. Y is given. So your x should be starting from y and go all the way to the right when x equal to 1. Right? So we will have y to 1. Okay. And what kind of y you can change? What is the possible range of y that you can choose from? And since our y is in the bottom 0, on the top 1, so your y can choose in between 0 and 1. Therefore your integration limit for the y will be 0 to 1. Okay, all right. Okay, now let's try it to see what happened. What is the possible result? 0 to 1. Okay, now I'm going to do the integration on x only. So y is the constant, right? So it should be a coefficient, and x is x to the power 1. So it's a power form. Therefore, we should have x to the power 2 with 1/2 as the coefficient on this particular integration form. Okay, and what else? No, we got nothing. Okay, so we should have 1 y to 1. And then we are going to do dy. Okay, okay, then you should do the plug-in. 0 to 1. So we have first term y times 1/2 minus 1/2 y squared dy. Right? Okay, so then we do one more time. 0 to 1, 1/2 of y, that's the first term, minus 1/2 of y to the power of 3 dy, right? After simplify. Okay. Now, 1/2 of y. So 1/2 is coefficient, and y squared 1/2 minus by 1/2 y to the power 4 1/4, and evaluate from 0 to 1. Okay, so what do we have now? A quarter, 1 minus 0 minus 1/8, 1 minus 0. So finally we have 1/8. A quarter minus 1/8. So it's 1/8. Okay. All right. And this option number 1 is the easier part. So I left that as your exercise. And you can expect you should have the final result equal to 1/8 as I have here. Okay. Any questions? Okay, the double integral function is simple, 2x. And the region is a little bit complicated. Okay, so let's try to figure out what the region really look like. Okay, all right, now in the regular sense, we have x, we have y, and x equal to y, that's 45 degrees, x equal to y, and y equal to 0, y equal to 1, and here we 1, 1, and this is y equal to 1, y equal to 0. And what happened to this? X equal to e to the power of 2y. Okay, and what is the curve? Okay, and we know when you say y is equal to e to the power 2x, it's quite simple, right? This is x, y equal to e to the 2x, and here we have 0, 1. Okay, now we have x equal to 2y, e to the power 2y. So we should flip our x and y. So the curve should be something different now. So this is x equal to e to the power 2y. Okay, and here we should have 1 and 0. Okay. No, actually this is not look like that one. This is 1, 0. Okay, that might be better. And this is a curve, x equal to e to the power 2y. Okay, and since the region is bounded by these 4 lines, 4 curves, so the integration region should be something like this. Okay. Now, when you take a look on this region, it's obvious belongs to type 2, right? Okay, it's similar to the region on the right hand side. So we should expect him h1, h2 in terms of function of y. Okay. So this is h1. And this is certainly h2y. Okay, so our integration certainly become 2x, and now we should fix y and integral on x only in the first step. So y is given, therefore we have dx dy, and integrate from x from y to e to the 2y, the h1 to h2, and the possible choice of y will be from 0 to 1. Okay, all right. Okay, now after you converting our double integral to the iterative integration, and we choose the order dy dx as the typical type 2 integration form, the equation number 21, then it's become straightforward. So let's go further. 0 to 1 and x squared y e to the 2y dx, sorry, dy. We have evaluated the integration in terms of variable x in the first step. So we from 0 to 1, e to the power of 4y to y squared minus by y squared dy. Okay. Zero to 1, e to the 4y minus y squared dy. So in the first one, e to the 4y 1 over 4 minus by y to the power 3 1 over 3, and plug in from 0 to 1. Okay, all right, now the first term, the quarter, e to the 4 minus by e to the 0 minus by 1 over 3, 1 to the 3 minus by 0 to the power 3. Okay, so finally you have a quarter e to the 4 minus by 1 over 4 minus by 1 over 3. Okay, so what do we have? Okay, 7 over 12. Let me double check for that. Yes, okay. All right. And for this particular integration, it seems that you cannot use in the order of dy dx, right? Or at least that won't be won't be convenient for you. Okay, if you really want to use dy dx in the order, then your region probably have to cut into 2 small subregions, and each time you're using dy dx in different integration limits. Okay, for this particular one. All right. Any questions? Okay. And well, probably the most difficult part will be get used to the function of y, which we're not really familiar with. Right? Most of the case, our function is in terms of function of x. But now in our double integration, quite often you might encounter express x in terms of y. So you are going to treat your function using different variables. Okay. Okay, any questions? Okay, and let's take a break. We are going to go to number 24 later. Okay, number 24 is extremely important because this one demos how to change your order in order to make the integration a little bit easier. Okay, so let's begin with the way they describe in the service. Okay, and at least I'm going to draw the domain of integration as they describe in here. And we do have y equal to 0, and we also have x equal to e, and we have y equal to ln x. So certainly here we should have e and 1. Okay, and we expect him this is 1 0 and R is bounded by these three curves, so it should be the interval of this region. Sorry, the region of the shaded part. Okay, and now what type of integration form we have? It's actually, we can thinking about this is upper function, this is lower function, so it's type 1. We might thinking about this is lower function, this is upper function, that become type 2, right? So we do have two options. But in order you use type 2, you have to use h function, which is x in terms of y. And our function given here is y in terms of x, so we might use type 1. Okay, and so let me begin with type 1. Okay, type 1 means fix x first. And while we begin with lower end to the higher end. So our function is y, and integration will be dy dx, and given the x, y will be starting from 0 to ln x. Okay, and the range for x to choose from will be from 1 to e. So that will be from 1 to e. Okay, all right, so we have our double integral written in terms of iterative integration. Okay, so that means we can do further. So let's try it. 1 to e, that is something we are not going to deal with in this moment. And we have 1/2 of y squared, and 0 to ln x dx. So 1/2 to the front, integral from 1 to e, and ln x to the power 2 dx. Okay, now you might feel a little bit hesitate because this is not the regular integration. Okay, so you probably have to apply integral by parts, right? Okay, so what are you going to do? Integral by parts. And let me say integral by parts. So let me choose u as ln x squared, and dv will be dx. Therefore, my du will be 2 of ln x times 1 over x dx, and our v will be x, right? So according to the integral by parts, I should have 1/2 uv x times ln x square 1e minus by 1e and the integration will be multiplication of these two numbers v du. So we have 2 times ln x dx right? Okay. So in the first part, 1/2 of, when you plug in e to the first one, we have e times ln e to the power 2 minus by 1 times ln 1 to the power 2. That's the first term. Okay. And minus by, since I have a 1/2 and I also have a 2, so coefficient become 1, and the integration will be from 1 to e ln x dx. Okay. So it's quite obvious the first term is 1/2 of e. And the second term. Now we are going to do integration of this part. Okay. And integral by parts again. This time, u will be ln x. dv still dx. Therefore, du become 1 over x dx, and our v become x. So we have minus of u times v, x ln x, minus by 1 over e, and x times v du, which is dx. Okay. So we have 1/2. Oops. Let me back to the. Oops. I forgot. Here should be 1e minus by e times ln e minus by 1 times ln 1 and minus by x e1. Okay, so finally we have 1/2 of e minus by e minus by here I should have a quote in here. No. Oh, yeah. One e minus 1. So we have 1/2 of e minus by 1. Minus by 1 or plus by 1? Oh, sorry. Sorry, I think this is plus. Okay, so we should have plus. Okay, yeah. Okay, so the final answer is 1/2 times e minus by 1. Okay, and as you can see, as long as you choose the order, your integration process has been decided. Okay, and well, the only difficult part in this integration format, you are going to encounter integration of ln(x) square. Okay, which might be a little bit difficult for some of you, since it has to be integrated by parts twice. Okay, and it might be better if you change order. So let me try to do the integration of this same question. However, I'm going to use the order of dx dy. Okay, now I am still using the same domain as they have in here. Here I have x equal to e. Here I have 1, 0. And here now I'm going to say, instead of y equal to ln(x), we are going to say x will be equal to e to the y. So x will be equal to e to the y. Okay, and I'm fixing y, given y, and x should be starting from the left to the right. Okay, so x with e to the y to e. Okay, all right. And what kind of y you can go through? Since here we have e1, so y can choosing from 0 to 1. Okay, and I'll let you finish that. And your integration in this situation still need to use integral by parts, but you only need to do once. Okay, so in this case, using dx dy might be quicker, but using dy dx, it's easy to write the integration form, but evaluation itself take a little bit longer. So it's kind of a trade-off. Okay, and for this exercise, well, you have choice, but sometimes you have no choice. Okay, and certainly you will see that in your review test. You have no choice. You need to change the order. Okay, so my requirement for you to make sure your capability is possible to do in such kind, I would suggest starting with the description, draw the picture and change the order. Okay, sometimes you might encounter some situation you're doing the integration with dy dx is impossible. However, if you change the order, become dx dy, it was solved. So for you, every one of you in this class, you have to learn this technique, how to change order. Okay, so this is a very typical example, starting with dy dx, and draw the curve like this. For instance, you might start with this integration form. And from here, you knowing that your x is between 1 and e, and your y is between 0 and ln x, right? So from this integration, you have this knowledge about the domain, and draw the curve, draw the domain, and try to reverse the order, become this format. Okay, and that's a very important technique, starting with one order, using the domain graph, converting to the other order. Okay, and sometimes, I shouldn't say sometimes, 100%, you will see one of this example, this question in your review test. Okay, you have to show your capability of changing order, and without changing order, you have no way to finish it. You have to change order. Okay, there are a couple examples of such kind. All right, and questions? Okay.